Hello, everyone. On behalf of Stantec, I'd like to welcome you to the webinar, Understanding the Potential and Challenges of Hydrogen. My name is Jerry Fraser. I'll be behind the scenes as your moderator today. For today's webinar, you'll notice that the audience members are on mute. We will continue that throughout the broadcast. If you do have questions, please go ahead and use the question box on your monitor and type your question in there. At the end of the presentation, we'll be doing a question and answer session. As well, a recording of this webinar will be available to everyone who's registered shortly after the webinar. I'd like to introduce you to today's presenters. Nathan Ashcroft is a strategy and business development manager with Stantec. He works on clean technology and energy transition. As well, Pietro Di Zano is a subject matter expert on hydrogen, petrochemical, and refining processes. With that, I'll hand it over to Nathan to start today's webinar. Nathan.
Thank you, Jerry, and good morning to everybody, or good afternoon to all the people listening in right now. We've got lots to talk about today. Our aim really today is not to talk about hydrogen at 10,000 feet, is to really get into some of the details and understanding of the potential and challenges of hydrogen. So I'm going to start off with a very brief safety moment. We're going to talk about some of the significant issues that we need to take into account when we're designing hydrogen-related systems. And we're really going to talk about why hydrogen now. Why are we talking about hydrogen more than we ever have done before, and why is the right time right now? And look at some growth scenarios for hydrogen going into the future here. And as we talk about producing more hydrogen, we're going to really get into the meat of this thing. And I'm going to turn over to my colleague Pietro then, who's going to walk us through the different process technologies of producing hydrogen today, and perhaps go through gray, blue, and green hydrogen. And we're going to understand the techno-economical evaluations of those. We'll also talk about what makes a hydrogen project attractive and what makes it not attractive, and what is the right hydrogen path. And then we'll come back to myself, where I'll talk about some key opportunities that we see given the work that we've done going forward. And we'll talk about some projects we've been involved with, and then we'll open up to some questions. So let's get started with our safety moment. Hydrogen, most abundant element in the universe, the lightest element in the periodic table, and very critically, holding 3 times more energy density than natural gas. With those factors in mind, when we come to designing systems of handling hydrogen, we have to be very careful. If you were to look at some hydrogen systems involving, for example, compression, storage, distribution, I wanted to flag a few things that we pay particular close attention to when we're designing around this. One is leaks. Hydrogen, very light element, can escape, if you like, so we have to have a lot of emphasis on leaks and seals and integrity to make sure that we have no leaks, and I'll talk about that a little bit more in a second. Also, given the energy density of hydrogen, energy storage, we're storing very large amounts of energy in tanks, bullets, vessels, and so forth, and including piping as well. So our pressure relief, pressure safety design, our hazard and operational process safety, we have to understand this very well. Something very critical as we're handling hydrogen on its own and with other components in pipelines and so forth is hydrogen metallurgy, and particularly hydrogen embrittlement. There's been much work about this over many years, and it's something we have to pay very close attention to. Lastly, flame. If we were to get a leak and have a hydrogen fire, for example, hydrogen burns are a very light blue color, and in the right lighting setting, the daylight setting, it would be very difficult to see it. That would pose its own risks and challenges. What I will say is, from a process design perspective, these are knowns with experience. There's no reason why we don't approach hydrogen with the same care and attention. It's not unlike any other flammable and combustible fuels. With that in mind, I would say with the right design, it is a safe, clean, and very versatile energy carrier. And let's move to why hydrogen now in our energy transition. We're talking more and more about hydrogen, but these are really the drivers, and I want to get into this and explain some background, and then we'll get to some forward-looking aspects here. Really, Paris Accord, the world came together in 2016 and signed an agreement to battle climate change and reduce greenhouse gas emissions across the world. A very bold and unprecedented goal to reduce the emissions by 30% by 2030. That was off of baseline numbers in 2005. So that's incredibly ambitious. All countries together, a few changes since then, but still it remains a talking point every day for countries moving forward. But here's the challenge. Approximately 75% of our global energy sources are combustible fuels today. And as we know, when we combust fuels, we release CO2 and greenhouse gases. So on the one hand, we've got to reduce our greenhouse gases. And on the other hand, we're relying on 75% of our energy sources from combustible fuels. So into this equation, we know into the future, we're going to see a growth in renewables. We also are seeing tremendous growth in natural gas, and we can all probably think of the amount of LNG projects that have come online in the last 10 years and are expected to come online in the next 10 to 20 years. But the real lever for us beyond this, for the last link of the chain here, is hydrogen. And we're using hydrogen a lot, but when we combust hydrogen, there are 0 GHGs. So when I look at our energy density, our combustible fuel economies, hydrogen is clearly going to play a very significant part. Let's look at the energy transition over the last few hundred years to maybe try and explain this a little bit more. So this is a depiction of energy usage over the last 200 years, going way back and forward looking to 2050 here. So back in mid 19th century, we were using wood, and then we moved to coal. Then over time, we moved to oil, and in recent decades, natural gas, and we move into the frontier of hydrogen. So historically speaking, with wood and coal, it was the fastest and cheapest. We got our hands on those, we burnt them, we created energy. Then as we've needed more and more energy here, we've expanded into petroleum. And now in this era, particularly post Paris Accord, rather than looking for, I'll call it the fastest and cheapest, we're looking for the lightest and the cleanest. And that's really pushing us towards, I'll call it the end of the line here, towards hydrogen as our last option. There is nothing beyond hydrogen, to my knowledge, in the periodic table anyway. So in this whole energy transitions, this slide, energy transitions are nothing new. But as we've moved towards the lighter and cleaner, the one aspect that we really have to consider here is it still the cheapest? And we can say hydrogen is not the cheapest right now. So we have to really understand the economics of hydrogen and pick the right path and focus on those technology areas in order that we can move in that direction. But it is growing. So let's have a look at some renewed interest here around the world and get into some of the details related to growth. Some evidence, a lot of evidence. 60 countries around the country have committed to a net zero economy by 2050. So if you assume that those economies today are using 75% of their energy production comes from combustible fuels, hydrogen has to be a part of that component. How much? It's difficult to say. Some other drivers, and these are linked. Renewable energy costs have reduced. For example, hydropower is reduced. Wind, particularly offshore wind, has reduced, and in a lot of cases solar has as well. And I'll probably add nuclear in there, though it's certainly not renewable. This, coupled with electrolysis growth put together for green hydrogen, which we're going to talk about here shortly, is really showing some real renewed interest in this area as well. I've highlighted some countries around the world here that have leading the way, not to say other countries aren't as well. I just indicated these. A number of these countries have outlined their national energy roadmaps. Japan, for example, has an energy roadmap, very clearly has hydrogen in their Korea does too. Major initiatives that encourage people to look at UK and Germany. I saw a recent article on the hydrogen network of pipelines throughout Germany. Very conceptual, but nonetheless a major initiative. And many of us would have seen more hydrogen vehicles coming online, whether it'll be light transit or heavy transit, where it's particularly suitable, and even ferries, shipping aspects. And I even saw an article last week on renewed interest on using hydrogen for airplanes. So with all this in mind, we are certainly moving towards more hydrogen, and I think the question then becomes, how much more hydrogen are we going to see in the next 30 years? So let's take a look at that. I took the source here from the bottom right-hand side, the Bloomberg New Energy Futures Hydrogen Economy Outlook. I'd encourage people to take a look at that. It's pretty representative of a few different other outlooks as well, and I like the different scenarios that it posts. Just for reference today, hydrogen, as we know, is truly a global industry, a massive industry, where we use hydrogen for many different aspects we're going to talk about here shortly. Big unit, we're using 8 ectojoules of hydrogen per year. Ectojoules, for the mathematically minded folks on the call, is 10 to the power of 18 indices, a lot of energy. Under the 2 scenarios in Bloomberg, if we had a weak policy around the world, and by a weak policy, minimal taxes for GHG and minimal incentives, the estimates in Bloomberg, and they do correlate to other estimates, see us growing from 8 ectojoules to 27 ectojoules of hydrogen. That's a growth of between 3 and 4 times in the next 30 years. That's very significant for what's already a large global commodity. The big dark imposing tower there with a strong policy, that is to say very strong tax penalties and very strong incentives to move towards hydrogen or zero GHG economy, sees the growth at 99 or 100, north of 10 times. Sometimes the truth is in between. But let's say if we even envisaged just the growth here to the weak policy environment, weak policy projection, we're still going to see a very significant growth in hydrogen in the next 30 years, the next generation. So the question then becomes, as I've looked through the different scenarios and the fact that we are moving towards hydrogen as this source of zero GHG, the question now becomes, what are the different pathways to make this economical and also carbon friendly, and where do these technologies sit? To walk us through this in some detail now, I'm going to hand over to my colleague Pietro.
Thank you, Nathan. Thank you, everybody, for being with us today. I'd like to highlight technologies that we're going to be using for hydrogen production. Hydrogen can be produced from different factor inputs. These include any renewable energy, such as hydrogen, hydropower, wind power, and solar power. Of course, electrolysis units can use power from electricity grid as well as from nuclear power plants. Can I have the slide before this, please? Thank you. As per the drivers mentioned earlier in the presentation, or other fossil fuels, hydrogen's use is expanding. The most visible demand vector is for mobility. It is being used for cars, buses, and trucks. It's being evaluated for ferries, trains, and ships. If hydrogen is going to be the vector that we want it to be, it's going to have to replace natural gas, and definitely in heating applications, as was mentioned in combustion. It's going to have to replace natural gas in residential heating, in commercial heating, and in industrial use. We are observing customers asking us to evaluate the use of hydrogen as an energy vector in greenfield mines and/or as battery systems in these mines. We're also being asked to look at hydrogen in the steel industry as a reducing agent. The last 2 applications are for the largest hydrogen users. The refining industry uses different types of hydrogen, whether it's from catalytic reforming, steam methane reforming, gasification, and/or recovers off gases from its own processes or from adjacent clusters. While it's integrating all of these hydrogen units and sources, it is still looking at green hydrogen because it wants to reduce its carbon footprint. It's also looking at use of hydrogen for its own furnace systems. The ammonia industry is also a large user of hydrogen, as it is fundamental in its input. While it has exclusively used fossil fuel-based hydrogen, some of its participants are looking at using clean, green electrolysis hydrogen because it wants to reduce its footprint, but it also needs to look at cleanly produced nitrogen. Presently, their problems include scale and intermittency of power. And just a few statistics. Hydrogen use for 2019 is estimated at 70 million metric tons, as we've seen. 1 to 5% of that total is via electrolysis. 99 to 95% of it is for using fossil fuels. In terms of applications, 90% of the hydrogen can be found in the refining, petrochemical, and the ammonia industries. 9% of it is for heating, and 1% of it is for mobility. We'll definitely hope that that increases. Now, I do come back to the factor inputs. Water is always linked to the production of hydrogen, whether it is produced via electrolysis, whether it's using natural gas and reforming or gasification, water is always going to be used. We'll be exploring this a bit later in the presentation. Gray hydrogen is defined as hydrogen that uses fossil fuels, and that is converted through reforming and gas shift reactions. This is usually in the steam methane reforming process. Gasification of natural gas or hydrocarbons such as residues, naphthas, and coal is a mature technology where any of these fuels are fed into a reactor with specific amounts of oxygen. Water is used to lower the combustion temperature and to reduce soot. Autothermal reforming is a mix of reforming and gasification over a catalyst bed. Now, how are you going to choose one or the other in your processes for whichever industry you're in? The use of these different processes will depend on the hydrogen type, whether you're using hydrogen, syngas, or carbon monoxide. Steam methane reformer has the highest steam to hydrogen carbon ratio. The gasification has the lowest. Whether the process can be compatible with the downstream industry is also a factor. The refining industry uses hydrogen exclusively, so it is favoring steam methane reformer technology. The petrochemical industry uses a mixture of hydrogen and carbon monoxide, so they favor gasification or autothermal reforming. Finally, the units have to have a scale to meet the customer's requirements. Refiners can use steam methane reformers from 3 to 200 million scuffs per day. Gasification is usually used when they need 25 to 75 million standard cubic feet per day. The petrochemical industry uses the ATR technology when it needs up to 500 million standard cubic feet per day. So it's very important to decide what you're going to do with it, how much you're going to need, and how you're going to do it. Now, the issue with these production technologies is that they all produce and emit carbon dioxide. And when you capture that carbon dioxide, that's how you define blue hydrogen technology. Steam methane reformers produce between 10 and 15 tons a day, of CO2 per ton of hydrogen. Gasification usually produces double that. And autothermal reformers produce in between those two extremes. In the SMR technology, we can usually recover about 60% of the total emitted carbon dioxide. That is because the carbon dioxide is within the hydrogen production stream. It is harder to recover the remaining 40% as it is emitted as flue gas in the reactor and in the reaction's furnace. It is important to ensure that the captured CO2 is either completely used or sequestered. If we cannot completely use it or sequester it, then we cannot define it as blue hydrogen. And this technology, capturing the CO2 from these technologies, are the only technologies that can provide the amount of hydrogen that we need at the scale that we need it and at the price that we possibly want to pay for it. Finally, I come back to water usage. I'll give you a rule of thumb for steam methane reforming technology. Water usage for steam production alone is estimated at 7 to 8 liters of hydrogen per kilogram of hydrogen produced. Water usage for the process is estimated at 15 to 16 liters of water per kilogram. And that's usually not recoverable. Water usage for cooling is estimated around 32 liters of water per kilogram of hydrogen produced. That will depend on where you're located, the temperatures and the regions where you're located, and most of that water can be recovered. Now, green hydrogen is defined by the use of clean power, usually produced by renewable energy, usually wind, solar, or hydropower. Grid power can be used if it can be deemed clean, although in most jurisdictions, such power is a blend of fossil fuel-based production power, using natural gas or coal, with a renewable power. We can include geothermal power in this definition, but it's still in its infancy, and where it is applicable, we don't yet know. Nuclear power can also be used, if not defined as renewable, because it does not emit CO2, but it does have its significant other problems. Now, green hydrogen is estimated to have cumulatively reached 250 megawatts of electrolyzer capacity. This equates to approximately 45 million standard cubic feet a day, or 50,000 normal cubic meters per hour. And about $350 million to $450 million has been invested in green electrolyzer technology to date. And we have seen announcements where approximately 3 gigawatts of green hydrogen projects have been announced for implementation between now and 2025. We believe that the use of excess power capacity from either renewable units, hydropower, or nuclear sources can provide the necessary low power costs required to introduce large amounts of hydrogen into target applications. We know that electrolyzer costs will reduce. We know that improved project designs and operation and higher load factors will further reduce hydrogen prices, although we do believe that they will continue to be higher than the gray and blue hydrogen costs in the near future, and we'll present you that later. The main area that this technology has to deal with is scale. However, the adoption of green hydrogen in some of the industries that we've mentioned, especially steel, refining, ammonia, will have to adapt their processes significantly to use green hydrogen. That substitution, that adoption will not be easy and will require a significant amount of money. I do want to note one water use again. Electrolysis will use theoretically 9 liters of water per kilogram of hydrogen. The freshwater amount that has to be handled for any project is going to be anywhere between 13 and 15 liters of water per kilogram of hydrogen, depending on the incoming water quality. So water availability can be an issue in some parts of the globe, especially if large volumes of hydrogen will have to be produced. At this stage, I want to highlight 2 technologies that are prevalent as electrolyzer technologies in the industry. We have the alkaline technology and the proton exchange membrane technology. The alkaline technology has been around since the 1920s, and the proton exchange membrane technology has been around since the 1960s. The alkaline technology uses potassium hydroxide as the electrolyte, while the PEM uses a membrane. The biggest issue that the alkaline technology has is that it cannot operate intermittently. Once it is started, it should be, it should stay on. It is able to produce much more hydrogen in units than the PEM technology, but the PEM technology is growing faster because of its ability to link itself to the renewable energy and its intermittency. Both technologies have a challenge in scalability, but I do know that the OEMs, the original equipment manufacturers, are looking at ways to expand their offering. They are now at around 2 megawatt units that are commercial and reliable. In terms of efficiency, I would say they're the same, using anywhere from 3.8 to 5.4 kilowatt hours per cubic meter of hydrogen produced. I think it's the developer's responsibility to determine whether they want to spend more capital to gain more efficiency. At this stage, we're not going to be talking about the solid oxide fuel cells. They definitely have a promise. They're not yet commercially available to any large extent. So at this stage, we will skip commenting on solid oxide fuel cell technology. I do want to highlight some macro factors enabling hydrogen implementation. We've alluded to the factors applying green hydrogen to meet society's needs. These factors need to be understood because that's the only way we will break some of the barriers. In general, the health of economies and public acceptance will have significant impact on green hydrogen implementation and adoption. Society will have to become more acquainted with hydrogen. The learning curves are steep, and the specifications will have to be applied to ensure safe and proper, reliable use of hydrogen. Now, society has benefited from the focus of the industrial companies I've highlighted before to deal with the technical issues of scale and infrastructure. But as hydrogen expands into the other industries that I've mentioned, especially for cars or heating, these issues of specifications will have to be addressed by different industries, entities, and governments. And within the infrastructure system, one item that needs specific attention is the need for power. There is insufficient power production at the moment to meet all of society's desires and needs for green hydrogen. There will have to be a complete revamp of power production and associated costs if we're going to go there. Just as an example, if hydrogen is to make the inroads required by the US to meet expected carbon limits by 2050, it will have to produce as much electricity as it presently produces for its whole economy. This does not include the energy and electricity it will need for its own growth of its economy to 2050. This is why we believe that blue hydrogen will have a place in producing hydrogen and decarbonizing our world. Synchronization of this vast amount of investment will have to be met with hydrogen demand scenarios that pull projects toward completion. And it is only through government policy and long-term support will we make this happen. At present, green hydrogen prices, adoption in a timely manner would require complete re-education of people's impression of energy costs. It is now too high to motivate full-scale substitution. Now, when we're working with our customers for green hydrogen projects, there is an understanding that they might have that green hydrogen projects are only made up of electrolyzers. And as we proceed to larger and larger projects, we notice that we have to include power delivery and conditioning and water supply and treatment into the mix. And then the produced hydrogen has to be compressed in order to be stored. That compression, its size and pressure will depend on the capacity and technology of the compression of the storage system and will also be a function of offtake agreements. There needs to be a proper assessment of the distribution of the hydrogen, whether it's by tube trailers or by pipelines. And again, this is dependent on the offtake agreements. We believe that the proper design, layout, and safety spacing of all of these components will reduce the CapEx and OpEx of these projects, which leads me to the project criteria we believe need to be considered to achieve project financing and operational success. What do we need to consider to make a project bankable? We've discussed the production technologies, and the project drivers. Now we need to look at what will make a project get over the financial hump. We need to ensure that company vision and its project drivers match. At times they do not, and those projects will not succeed. Technically, we need to look at technology that we need to select for the project and the equipment suppliers. They all have different specifications. They all have different product attributes. They all have different corporate positions. The projects also have to ensure that they have sufficient power as cheaply and as reliable as they can get. That is not easily available. What do you need to do to get it to your project? And how do you get it there? And at what cost? And then we need to think about storage. Commercially, and this is very important, there are different hydrogen prices depending on the customers you sell it to and the industries you sell it to. The differences are sufficient that they can make or break a project. Add this complexity to the load factors of a plant, and we can easily become disenchanted or completely enthralled by such a project. Finally, if we put all of these things together, we will have a narrative where we can explain and justify the required funds and also get government subsidies. Before I pass the baton on to Nathan to discuss some of the project opportunities we're seeing, I'd like to just present a commercial evaluation that we've done comparing green hydrogen to gray hydrogen and to blue hydrogen. We've taken the position of using it for a project of 20,000 cubic meters per hour, which is equivalent to 100 megawatts of green hydrogen. In terms of units, you would need 50 electrolyzers to match the one steam methane reformer that you would need both for the gray or the blue hydrogen projects. In terms of CapEx, we've estimated at $75 million for the electrolyzers, $55 million for the gray hydrogen SMR, and $71 million total installed cost for the blue project. Now, I do want to highlight very specifically that the green hydrogen project does not include the capital required for ancillary units that we've mentioned before. And that can easily be as large as the electrolyzer capital that we've highlighted there. We also want to highlight that the electricity price has a definite impact on the final price of the hydrogen, green hydrogen. So we're looking at prices for electricity at $10 per megawatt and $50 per megawatt. Our natural gas assumption for the steam methane reformer is set at $1.8 per gigajoule. Finally, the load factors are very important in the green project. We've set it at the minimum of 20% and a maximum of 50%. For the gray and blue projects, these are usually quite large. They usually have their own customers, and they are usually asked to operate very close to 100%. For this economic exercise, we've set the duration of the project at 15 years. And if you look at the final results, the hydrogen cost for the green project would range between 1.6 and 5.2 US dollars per kilogram versus 1.1 all the way up to $1.7 per kilogram in the blue project. I do want to reiterate one more time that the hydrogen for the green project costs are not including the ancillary capital. We also are not including for all three projects the capital required to pipeline or the loading factors, the loading equipment to load tube trailers. So it's not outside of the we have not included the capital outside of the battery limit. Thank you for your attention, and I pass it back on to Nathan.
Thank you, Pietro. So we've walked through the hydrogen scenario around the world, why we're moving in this direction and where we see the growth. And Pietro's walked us through the gray, blue, and green and the different economics and the different scenarios, and it's quite often different jurisdictions in different countries. So I want to focus on some real key opportunities that we see on hydrogen that's really making sense from the work that we've been doing and continuing to do. Some key areas of opportunity where we have an abundance of low-cost power from hydro, offshore wind, particularly focused on here, and also nuclear. Where we have those in place and that good infrastructure in place, and as we mentioned, access to water, we're seeing more and more of those projects, and I'm going to pick one out as a case study here shortly. We expect to see quite a bit of growth in that area, coupled with the intermittency operation of the PEM electrolyzer. This is a natural fit, and we're seeing growth in this area. Given the requirements to produce more hydrogen at a lower cost, we're seeing people trying to do things in a novel way, such as underground in situ gasification, reforming, and we have another project and technology we want to highlight there. So there's room in this equation for novel technologies, and we want to talk about one. Blue hydrogen, essentially the elephant in the room on the production and the scale of hydrogen today. So if you consider for blue hydrogen, we need availability of natural gas, and we also need availability of users nearby for hydrogen, and also the ability to capture and sequester the CO2 in the ground. You start to look at, I'll call it energy hubs around the world, industrial parks, and I think of in Western Canada, the Alberta Industrial Heartland, home to tens of billions of dollars of multinational companies with a variety of energy and petrochemical facilities. There's an abundance of natural gas in that area, and there's the ability to sequester, and it's being sequestered, CO2. So these areas around the world that have the ability and have access to natural gas and the ability to sequester CO2, we will see a lot of growth in this area, perhaps with retrofitting existing grey hydrogen production facilities with carbon capture infrastructure. And on here as well, an area that we're seeing growth in around the world actually is around what's phrased as HENG, hydrogen enriched natural gas. So as we look to our networks of pipelines, whether they be to industrial facilities or even to our homes, where we're burning natural gas, the ability to blend in hydrogen to various amounts into these networks to lower the GHG output at the end is very real. We're seeing a number of pilots in Europe, some in North America, and quite frankly, we're going to see a lot more of this. I'd flag to the listeners the points that I raised earlier in my safety moment. This is an area, depending on the blend rate, that has to be evaluated from an asset integrity and metallurgical and system integrity perspective very carefully, where this is totally doable. So now I want to move to talking about a couple of areas and some projects we've been involved with that are very interesting and very exciting and make a lot of sense. Image on the right-hand side here, a conventional hydroelectric facility. Two things that we can see in there: hydroelectric facility and abundance of water. I guess a third thing, the electrical power outlet. So as we discussed previously, to produce green hydrogen, we need a low-cost electricity power source, which we have here. We also need access to water, which we have here, and you've also got the power availability here. So if you were to consider on this landscape, perhaps a short distance away from here, we have, if we were to place the electrolyzer and associated infrastructure to run the electrolyzer, these type of projects make a lot of sense for us. And if you could have, as Pietro talked about earlier, the offtake agreements long-term for hydrogen, say for local industrial users or blending in a pipeline, these projects are making more and more sense, and we'll see more of these. And we are pretty much on a weekly basis with people asking for studies and seeing how this comes together. The next item I want to talk about is the novel approach. And as we discussed earlier with the amount of hydrogen the world could absorb and use it if we could produce it on a cost-effective basis, there's room for novel approaches. And I'd like to flag a company here that we've been working with, Proton Technologies. Proton Technologies are based in Western Canada, and go on their website for a more detailed explanation, but they're looking to do something in a very novel way. An air separation unit above ground with oxygen injection deep inside an oil reservoir, and I'll call it an in situ reaction to keep the complicated conversation to a minimum, where the only element we bring to the surface would be hydrogen for cleanup, compression, storage, and distribution. So this, in principle, is having the reaction underground in areas where there's a hydrocarbon and only bringing hydrogen to the surface, and we capture the carbon in the ground. There's trials of this technology going on in Western Canada right now, and Proton would be able to fill in you with more details. Some of the early work that we just completed involved a sizing of air separation units, optimizing oxygen injection technology, and also hydrogen cleanup, compression, cleanup, compression, storage, and distribution. So keep an eye on for this one. Very, very interesting. So today we've covered a lot of ground, and our aim really was not to talk about everything at a 10,000 feet level, which is quite often the case with hydrogen, but to really get into some of the details and project evaluations, and to be quite honest on some of the challenges with green hydrogen, but also to flag some of the areas where we're seeing a lot of this potential. We have lots more to share, and we'd be interested in hearing people's comments in general on the webinar, and potentially perhaps hope having another webinar to talk about some more technical details and a deeper dive on economic aspects of hydrogen production. But I think at this point, with I think 18 minutes left, I think we'd like to open up the floor to some questions and get into some of the details here.
Thank you, Nathan and Pietro. That was very informative. We have a number of questions that have already come in through the question box, and I would encourage folks to type their questions in if you do have some specific questions that you'd like to ask the presenters. Let's start with a question on Henge. Vince Reardon asks, would Henge pipelines be used to deliver to homes in LP gas distribution or only in the high pressure distribution? The reason he's asking is he wonders if valving is valving rated for tightness required of the hydrogen molecule, for instance, the valve on my furnace, hot water tank, barbecue, and so on.
That's a great question. I wish some of our asset integrity metallurgists were here. I think that definitely the amount of changes that we have to do, whether it's LP or HP, on our different systems need to be evaluated on a case-by-case basis. But there's no question we'd have to make some changes. I think on a very low blend rate, some work that our metallurgist did, and by the way, in the second webinar, that's something that we'd potentially want to cover in more detail. I think on a low pressure, a very low blend rate, I think the changes could be minimal, but as we look to move towards north of 10%, certainly north of 10%, I think we will have changes to our infrastructure on the piping throughout the chain, all the way through to our furnace and end users. Anything to add on that, Pietro?
No, yes, please. These are some of the trials that are happening worldwide, and I did refer to the changes that will have to be done in terms of specifications across the use chain. We've talked about the production chain now, but across the use chain, the same amount of asset integrity, specifications, and changes will have to be looked at. So it's a very good question. It is pertinent. It is relevant. And it's also going to be part of the public acceptance that they're going to have to be comforted that they won't have those leaks.
Terrific, thank you both. I just will remind all of our attendees that yes, indeed, we will be providing a recording of this webinar after the presentation. There have been a number of questions regarding that, so that will be sent out shortly. Our next question is, what is your opinion and what can you say about green hydrogen production from natural gas decarbonization, removing carbon prior to combustion?
Could you repeat that question again? Sorry, Jerry.
I sure can. What is your opinion, or what can you say about green hydrogen production from natural gas decarbonization, removing the carbon prior to combustion?
All right, so we're talking about NGD, natural gas decarbonization from natural gas. That wouldn't be, unless it was a renewable natural gas on the feedstock, that wouldn't be a green hydrogen. We recently did some work on natural gas decarbonization on the landscape of those different technologies. If we had more time, we could have opened up on that on the novel technologies aspect as well. That's a technology branch where we're splitting natural gas into hydrogen and a form of synthetic carbon as well. So there's trials of this underway. I think it's entirely possible. I think the work that we did on a mass basis, if I recall, it was something like 3/4 on the mass would be carbon products. And the work that we did indicated you really need to have a market for that carbon. If it's going to become a synthetic carbon, then there's tremendous market and growth for that as well. So we're certainly interested in it. We're trying to see how the trials are going ahead. There was the Hazer process in Australia. We're pushing ahead with this, but it wouldn't be green hydrogen unless it was a renewable natural gas on the front end, and I would question the volume of it then. Anything to add, Pietro?
I think you've hit the spots. Having to deal with the amount of carbon that would be produced is something that people have not yet taken into account. With everything that you do in the novel technology adoption, there's always a consequence that you have to deal with that you may not have thought of. And in this case, it's the carbon. But I think it has potential, but it is not yet commercial.
Yeah.
And I think we can still deal with all of the issues of the green hydrogen better at the moment than having to deal with that.
Yeah.
Our next question is, at the start of the presentation, there was a mention of limited use for hydrogen in mobility. Looking out to 2050, what do you see the range in I believe it's in percentages of overall hydrogen use for demand for mobility uses? So I believe it's, what is the percentage of use of hydrogen in mobility?
I'll cover it briefly and I'll turn over to Pietro. The Bloomberg report in particular, we simplified it. I can't remember which slide it was, but I showed the different projections to 2050. Major growth was predicted in the mobility sector and adoption of hydrogen. I think it was, I would say 25% of that large column. Right now, it's a very small percentage. So if we're going to see the proliferation and growth of hydrogen, it's a very significant percentage. The transportation sector really needs to adopt. Pietro?
Yeah, I want to take a different tack on this. The use of green hydrogen in the ammonia industry and the refining industry or the petrochemical industry is going to be difficult. We don't have the time to look at all the processes that need to be changed or adapted to using green hydrogen. But they all have stranded assets. They have, they cannot change over their assets and produce what they were producing in the first place. So they're going to be, they're going to be last at adopting this. And if governments want to increase green hydrogen use, residential use, as we've mentioned in the Henge, or mobility will be where the governments have to push. And that percentage is hard to come by because it's based on how much policy there will be, the ability for the industry at the renewable power industry to reduce its costs, the electrolyzer people to reduce its costs, and what type of incentives or penalties the governments will impose so as to push hydrogen use in cars or trucks or ships. I think what you really need to look at is those three things: the cost of electricity, renewable electricity, the cost of electrolyzers, and the policies that, and I should also include the cost of cars, but really how the government policies will push that, that's what's going to determine how it's going to be adopted and how quickly.
That's terrific. Okay, our next question. comes from Ian Park. He's asking, where do you see the progression of hydrogen in power generation through fuel cells, turbines, or reciprocating engines?
Oh, another good question, very detailed. Pietro, do you want
Wow.
to take that on?
Yeah, thank you, sir. It's an interesting application. Essentially, what you're trying to do is using renewable power to make hydrogen as a storage of battery storage, and then converting that back to where you need it into power. The problem is that you have efficiency losses across the whole process. And when you do the calculations, however the assumptions are, when you do the calculations, you're easily close to using natural gas thermally in terms of efficiency. You can easily reach efficiencies of 35 to 40%. So the use of hydrogen in that application definitely needs to be justified along different lines. It can't be justified on efficiency terms. It has to be justified whether it's somebody has a remote area and cannot access natural gas or other or alternatives, or has specific needs, intermittent needs, and needs hydrogen for a very specific item. We can discuss efficiency issues at infinity, and it becomes very personal and very subjective. It needs to be looked at in those terms.
Right. Our next question is from Marvin Polis. For transportation applications, does it make more sense to use fuel cells or to combust the hydrogen? Do you have a comment on that?
I'll cover where I know, and Pietro will know more than I do. There's challenges with using hydrogen on internal combustion. I think the fuel cell path with hydrogen is well identified as the path of least resistance due to the combustibility and all sorts of different aspects of hydrogen in combustion engines. Pietro, do you want to comment further on that?
Yes, I do. There have been examples where motors have been converted to use of hydrogen. Well, they started with the use of natural gas and then the use of hydrogen. The efficiencies on those motors drop significantly. The reliability drops significantly because the industry has been using gasoline or diesel, and it's been designed for that. It doesn't mean that those problems can't be overcome, but they will need to be overcome. However, if we look at using fuel cell technology and having electricity for powering the motors for the cars, I think there's a better efficiency argument to be made and a better lightweight use of lighter weight of materials, and I think there's a better argument to be made using fuel cells than using or converting the internal combustion engine to using hydrogen. I don't have specific numbers. I have seen the conclusions of the reports at the moment, and the conclusions of the reliability issues at the moment. But if that person needs more detail, I'm sure we can get more information for him.
Great, thanks, Pietro. Our next question is, can hydrogen be used for storing energy for intermittent power sources, such as solar and wind? And for instance, are there gas turbines that can burn hydrogen?
I would say yes. I mean, the intermittency, well, if you're producing from natural gas, or the intermittency of the membrane technology to store hydrogen in a compressed quantity for intermittent power use afterwards, yeah, it's certainly an option. It depends on the application and putting those pieces together for the project evaluation. But if you've got power, or if you've got natural gas, you can, as we outlined earlier, you can produce the hydrogen, store it in large energy quantities, and use it as you want. I think that becomes a question of storage. Whether it's in vessels or in very large, some work around the world, very large storage underground in cavern type structures.
I'd like to
Okay, that
add.
leads to a, oh, sorry, go ahead, Pietro.
Yeah, I'd like to add something there. I think this is a good rationale, a good logic to bring in blue hydrogen. Because you have scale with autothermal reforming and or steam methane reforming, you can produce the amount of hydrogen that you need to burn into a gas turbine to produce the electricity that is needed. And in that case, you're not losing the inefficiencies going from renewable power to hydrogen back to power, which was an earlier question. In this case, you would be producing the hydrogen via natural gas or some fossil fuel, storing the CO2 as best we can, and then using that hydrogen and decarbonizing the whole system. The second question that was highlighted by the person was, do we have gas turbines that can do that? Yes, GE and Siemens, and I would assume the others have developed and or are developing turbines that will use hydrogen exclusively. That is not something new. There is that option. The option in this case, though, we need to deal with is the sequestration issues. Society has not yet come to terms with it, legally or commercially, or from a government point of view. There are a whole bunch of other things that need to be dealt with, but that I think is the only way to deal with it. Dealing with it with renewable energy and electrolyzers, you're going to have an efficiency issue that I don't know if society wants to deal with.
Okay, thank you. There's a bit of a follow-up question, but it comes from another person. Their question is there currently an industry preference for hydrogen storage solutions? For example, tanks versus the salt caverns?
Pietro?
I think, yeah, I don't think it's a binary choice. It depends is very important. In areas like the US Gulf Coast, areas in Alberta, near the Alberta Industrial Heartland, you can have caverns that were developed because of salt mines or just because of the geology. There are also this type of storage capacity in Northern Europe, Rotterdam, UK area, English Channel area, can be done, can be stored. But you don't need just that. You need to look at whether it's all part of the full chain. I don't think it's a binary decision. It's a project by project, geography by geography, region by region, and that's how you're going to make your decision.
Great. Next question is, does saltwater versus freshwater have a significant effect on the green hydrogen process?
Yes, Pietro, do you want to take that?
Well, at the moment, they're all looking. Well, no, not all looking. There are saltwater electrolyzers, but in general, people are looking at the very cleanest of water systems, so that we don't have corrosion of the anode and cathode and across the whole system. So at the moment, the preference is for the cleaner the better, and the fresher the better.
Even demineralized.
Yes, to that extent.
Yeah.
Okay.
But I know why the gentleman or that person is asking that question. It would solve a lot of problems, but at the moment we're not there yet. Not that I know.
Yeah.
All right. Next question is, what is the business case for developing countries like Nepal, which are rich in hydropower? How much would a pilot cost to demonstrate?
That's a really good question. We do work in Nepal. I think it's a question we want to take offline and understand what can be done. But the beauty of, as I discussed earlier, the hydropower link there is the access to conceptually low cost power and also the access to water. And the electrolyzer technology can come in a skidded package with equipment around it on a small scale that would go close to a pilot. So it's something that can relatively easily be done. So I'd want to take it offline on what the cost of that would be, but the concept of doing that where you already have that infrastructure around hydropower and water is relatively straightforward, but we'd need to obviously cost that up.
I'd love
to.
Please
send us an email directly on that.
Yeah, I'd love to do a project in Nepal.
Yeah.
Terrific. We are at the top of the hour. That's the end of our time. We have a number of questions left in the queue. I'm going to pass those along to the presenters and have them follow up directly with the folks that are asking the questions. I want to thank everyone for joining our webinar today. And again, thank Nathan and Pietro for sharing their expertise on this subject with us all. A reminder that we will be sharing a recording after the presentation. It will be sent directly to each of you. So thanks again for joining us, and we appreciate your patronage.
Thank you. Aye.
Stand by one moment.
Okay.